Okay, so today what I want to talk about is the concept of expected value for continuous random variables, right? So basically, expected value for continuous random variables. Right, so you remember that we introduced this concept for discrete random variables, and basically we learned about things like the mean and the variance and things like that. So now what I want to do today is just kind of extend that idea for the new random variables that we just learned about, right? So it's actually very similar. So recall that for discrete random variables, what we did was we defined this quantity called the expected value, and that was basically the sum over all the possible outcomes of that random variable. The outcome times the probability of getting that outcome. Right? So this was the PMF, the discrete PMF. And so for continuous random variables, all we're going to do is swap out this sum for an integral, right? Because now we don't just have a discrete set of outcomes, we have an infinite number of possible outcomes, right? And so what's that going to look like? Well, I'm just going to write it over here. For continuous random variables, we basically swap out the sum for an integral, right? So the expected value of x is going to be defined as the integral over all the possible values of the random variable, the value times the probability, little f, of, well, not the probability, the PDF at that value, dt, right? So this is the PDF of this random variable x. Same kind of idea, right? All we're doing is we're multiplying values times PDFs, okay? And then we're integrating those up. So instead of adding them up, we're integrating them up. And just for completeness, this definition is really exactly the same thing as this. So in some sense, what I did was I first introduced the concept of expected value when it was easy to think about the possible outcomes. But let me just show you a quick derivation to prove that this and this are really the same thing. So let me just say that if x is a discrete random variable, then basically the PMF and the PDF are the same thing, right? So if I'm being a little bit more explicit, what I have is something like this. Again, looks a little bit nasty, but all this is saying is that the PDF, I can make basically a PDF out of the PMF values, right? Because what I have is I have a bunch of delta functions centered at the possible outcomes, and each of these guys has the height, the probability of getting that outcome, right? And so on. And so if I plug that into here, what I get is that, so the expected value of x, I defined it here, is t times the PDF dt. Now I plug in what I have here. So here, now the PDF is really just going to be a bunch of scaled and shifted delta functions. So I'm going to have t times this sum. Then I do the old trick of switching the sums and the integral. So the sum comes to the outside. and then what's, this thing doesn't depend on t here at all. Then I have the integral, minus infinity to infinity, t times this delta function that's firing at xk. And what you should remember from signals and systems is that when I integrate a delta function, right, the only thing that happens is I take where the delta function fires, and then I evaluate whatever the delta function is multiplied by at xk, right? So this is going to basically be saying the outcome, or the result of this integral is nothing but plugging xk in for t. And this is exactly, what I defined over here, right? This was my original definition of expected value from maybe lecture 6 or 7, and I see I get the same thing. So really, all I'm doing is now you know the grown-up version of expected value, right? So in theory, I could have started with that in the very beginning, but I think it would have been really confusing because it's useful to think about coin flips and die rolls and so on when you're first learning about probability. So basically, this is the same thing as before. Okay. All right, so let's do some examples. So basically you can see that expected values are going to involve doing a bunch of integrals, right? So something to do on homework 11 is, a bunch of integrals by hand. You can always use something like Wolfram Alpha to check your work, but keep in mind you're not going to have Wolfram Alpha on the exam, right? So you got to get used to some of those integrals that you probably haven't thought of since maybe Calc 1 or 2. Now, like I said, I'm not trying to throw crazy integrals at you, so we're talking about polynomials, exponentials, things like that. But, you do have to be quick enough to be able to solve these things in a short amount of time, right? So I'm going to do some integrals today that hopefully will remind you of the stuff that maybe you should be remembering. And I think that the homework will also help brush up on that. So the easiest problem is something like the expected value of a uniform random variable. So expected value of a uniform random variable. Let's remember, what does the PDF for that look like? So basically it says, okay, between A and B, I have this PDF of this height. This is my PDF, right? And the area under the curve is 1. That has to be true for a PDF, right? So I already kind of suspect I know what the answer is going to be, right? The answer I kind of expect is going to be halfway between these 2 points. I should basically expect that to be the average, but let's kind of show why that's true. So the expected value of this random variable is the integral from minus infinity to infinity, t times the PDF dt. Now here, this thing is only defined, it's only non-zero between A and B. So I can immediately turn this into an integral from A to B, t, and what is the PDF in that area? It's 1 over B minus A, dt. Now I do the integral. I've got the 1 over B minus A comes out because that doesn't depend on t. Then I have a 1/2 t squared, and I evaluate that at t equals B and t equals A. And so my result is 1/2 b squared minus a squared. And then I see that this b minus a goes into this guy here. This is just 1/2 b plus a. And so that makes sense, right? That says basically the expected value of this distribution is this middle value. It's the average value between the endpoints. So I pause and ask, any questions about this? So the intuition here should be good, which is the sense that if I have a symmetric PDF, right, one that has basically, it's a mirror image around some middle point, then I do expect that the expected value is going to be that middle point, that place where the mirror image is happening, right? So let me just prove why that's true. So in general, the expected value of kind of some sort of symmetric PDF is equal to the middle point. Let me show why that's true. Well, here's a slick little way of thinking about it, right? So suppose I have some sort of general PDF, you know, let's just kind of make some arbitrary shape. And let's suppose that it's centered around some number mu, okay? So this, this PDF is, you know, remember from signals we also talked about even and odd functions, right? So here, this PDF I've sketched is an even function with respect to mu, right? With respect to that possibly non-zero value, okay? And again, what this means is that, you know, there's half of the PDF is under this part, half of the PDF is under that part, and everything is nice and symmetric. Now let me think about what is this function. This function here is, so let's see, this is going to be, I'm going to call this function t minus mu. Okay? So if I were to plot that function, right, at mu, it's equal to 0. When t is greater than mu, it grows linearly. When t is less than mu, it goes linearly the other way, right? And so this function I can see is odd around mu. So what do I get when I multiply these things together? So let me think about what do I get when I multiply t minus mu times this PDF. What will it look like? Well, it's going to change the shape of the curve in a certain way, right? So it's going to be 0 in the middle, and then it's going to do something or other on the right side, and then it's going to do something or other kind of like reverse on the left side, right? Because this is even, this is odd. When I multiply even times odd, I get an odd function, right? And what that means is that, you know, this area and this area are going to be the same, but one is going to be positive and one is going to be negative, right? So these things are going to cancel each other out. Why do I care about this? This is a different way of saying that if I were to integrate t minus mu times this PDF, I should get 0, right? Because the area on the right-hand side is entirely canceled out by the area on the left-hand side. And if I accept that that's true, then I can take this apart and I can say, okay, well, what does this tell me? This tells me that t f of x of t equals this integral here, mu times f of x of t, dt. I guess I should put some dt's here. This thing here is just the expected value of x by my definition. And this thing here is going to be basically mu times the integral of the whole PDF, and the integral of the whole PDF has to equal 1, right? Because this whole integral has to equal 1. So what did I learn? I learned that, you know, I set this up so that I was symmetric around a certain value, and then I derived that the expected value of that distribution had to be in the middle, okay? So generally that kind of makes sense. Hopefully that stands to reason, right? And now we know, in some sense, why was it that when I defined the Gaussian distribution, I used these symbols, you know, mu and sigma, right? So remember when I defined the Gaussian distribution, I basically said, oh, it looks like this, right? And I guess I'm going to derive this. Am I going to derive it? So, I mean, I guess I don't have to derive it because now I told you that, you know, okay, since this thing is symmetric around mu, that this, in fact, is the mean of the Gaussian. Okay? So that's why we called this parameter mu instead of calling it L or B or some other weird number, because we knew in the end it was going to become the mean, right? Okay. So let me do a, you know, non-symmetric PDF, okay? So what about something like, you know, this is a PDF 3/8 t squared when t is between 0 and 2, and 0 otherwise. So that looks like a piece of a parabola, right? Kind of going like this, and then it stops at 2. Well, first of all, just to practice, let me just kind of ensure that this is in fact a PDF, right? So I need to kind of prove to myself that when I integrate this thing, I should get 1, right? And so here I'm going to integrate between 0 and 2, 3/8 t squared dt, which is equal to 1/8 t cubed, evaluated at 2 and 0. I plug in 2, I get 8. I plug in 0, I get 0. And I get 1, right? So I just kind of made sure this is a PDF, okay? This is, again, an example of one of those things where I could ask you on an exam, okay, you know, I don't tell you the 3/8 part. I ask you, okay, let's call this a t squared. Find me the value of a that makes this a valid PDF. That's a common kind of exam question, but here I'm doing it automatically, right? So now what's the expected value of this distribution? Well, again, a quick eyeball should indicate that, you know, I expect the expected value of this thing to be greater than 1, right? Because more of the probability mass is on the right-hand side than on the left-hand side. So I expect it to be kind of skewed somewhere off to the right. And so let's just kind of show what that is. Now I'm going to do this integral, minus infinity to infinity, t times the PDF, which would be, I guess, between 0 and 2, t times 3/8 t squared dt. So I got this integral, 3/8 t cubed. So now I'm going to have 3/32 t to the 4th at t equals 2 and t equals 0. So 2 to the 4th is 16, so I'm going to get the cancellation with the 32. So I'm getting 3/2. Right? And that tells me that the mean is somewhere over here. Which again kind of matches with my intuition that it shouldn't be, you know, shouldn't be in the middle. So let me pause and ask, any questions about this? Very similar to what you're going to be doing on the next homework. It won't take you a week to do these integrals. Okay, so let's go and talk about the exponential random variable, right? This is one of the ones we learned about last time, this new important named random variable that is useful for modeling things like the inter-arrival times between events, right? So let's kind of prove what is the mean of that, okay? So let's do the exponential random variable. Well, let's remember, what is our PDF? It's going to be lambda e to the minus lambda t for t greater than 0. And so there was a comment at some point about, could you please use t's instead of x's? And so here I'm trying to do that a little bit. I mean, again, whatever parameter I use here doesn't matter. I could use u, I could use x, I could use whatever. But here I'm trying to make it a little bit more t friendly. So what is the expected value of this guy here? Well, I have to integrate from 0 to infinity t lambda e to the minus lambda t dt. Well, this is a case of not obviously how to go about it. So now we have to use something like our old friend integration by parts. You remember that guy, right? So I basically, let's remember what is integration by parts, right? So if I have something like this, integral of u dv, this is equal to uv minus the integral of v du. So here, what am I going to do? U, I'm going to choose as t, which means my du is dt. V, or my dv, I'm going to choose as lambda e to the minus lambda t dt, which means that my v is going to be equal to minus e to the minus lambda t. So then what do I get if I apply this to here? Well, I'm going to get the integral, or I'm going to get uv t minus t e to the minus lambda t evaluated at t equals infinity, t equals 0, minus the integral of v du, which hopefully is easier. And so what do we get? Well, let's do this part first. So when I plug in t equals infinity, even though I've got an infinity here, this infinity in the exponent is going to take that, that exponent is going to wail down on that polynomial to be 0. So basically, there's going to be a fight between two infinities in some sense, and this exponential is going to win. So when I put in infinity, I get 0. When I put in 0, I've got 0 times 1, which is also 0. So basically, I got some zeros. And then over here, I've got this new integral, e to the minus lambda t dt, which is a lot easier to do. So I'm going to get minus 1 over lambda, e to the minus lambda t, t equals infinity, t equals 0. Again, I plug in t equals infinity, I get 0. And then I plug in 0, and I get minus 1 over lambda. So the conclusion is that the mean of the exponential random variable is 1 over this exponential parameter, okay? Now, just like in the previous discrete random variables case, once we prove something, or once you see it in a table in the book, you can use it, okay? So my goal is not to bludgeon you with having to do these integration by parts every time you have to do an expected value. You can sight read and say, okay, expected value random, or expected value of an exponential random variable, 1 over lambda, that's the end of the story, right? So it will be very clear when I tell you that you need to derive something versus when you can just use it from the book, okay? So let me pause and ask, questions or comments about this example? Like I said, you may have to dust off this, I don't actually know that there are any integration by parts examples on the homework, so you maybe got lucky on the homework. And I'm not going to, do something crazy on the exam. So this is more of an instructional thing than it is a sweating about integration by parts kind of thing. But this kind of makes sense. Let me just say that, remember that, when we originally defined this kind of parameter in words, we basically said that lambda was the, basically, expected number of arrivals per second. And so it kind of makes sense that the expected value of x is basically, it's like the opposite of this, like the expected number of seconds per arrival. So it kind of makes some sense. Oops, I'm sorry, I know you can't read this. Some intuitive sense. Okay. So there are, I'm sorry, you still probably can't read this. There are some, what's the right word? Malicious, awful random variables. Some random variables, it turns out, don't have means. There's a random variable called the Cauchy distribution that actually doesn't actually even have a mean, because when you do this process, you don't get anything that converges, right? But everything that we do in this class is going to be fairly well behaved, okay? You'll get a number at the end. Okay, so a lot of times we are interested not only in the mean of the random variable, but also in the expected value of some function of that random variable, right? This happens a lot. So for example, I tell you something that's random, and so I tell you that, okay, this signal is random, and I want the expected value of the power of the signal, and the power of the signal is related to x squared and not x itself. Or I say, okay, I'm going to give you a sinusoid that has a random phase, and then I want you to tell me the expected amplitude of it, right? So something where you're kind of relating a, one parameter to another. Or you say, okay, I am quantizing a signal. I'm going to do a whole quantizer example at the end of class here. And so that's going to introduce some sort of quantization noise that I can characterize. And then I want to know what is the expected value of the signal-to-noise ratio, right? Something that's a function of this noise. So again, the expected value of a function of x is something that we come across more often in a way than the expected value of the random variable itself. So we often want to compute the expected value of some function of a random variable. right? So for example, I tell you g of x, which is a way of taking whatever the random variable is and giving me some other number. And then I want to compute the expected value of this function of x, which is nothing more than, instead of plugging in x itself, I plug in this function into my formula. Right? So when this thing is t itself, right, or when, I'm sorry, when this thing is x itself, right, I want to know what the expected value of the random variable itself is, then I get the same t times the PDF I had before. But if I want to know what the expected value of x squared, then this would become t squared, something like that, right? And so, for example, let's suppose that in my, previous PDF case, let's suppose I had like this PDF from before, 3/8 t squared between 0 and 2. I could ask, okay, what's the expected value of 1 over x squared? Well, what I would do would be I would plug in this function, replacing it with t, 1 over t squared, times the PDF. And you can see here I've chosen this to be a particularly nice situation. I guess these integral limits become from 0 to 2. Everything cancels out, and I get from 0 to 2 integral of 3/8 dt, so I get 3/4. Right, so here, this is just, an example of working a simple function of the random variable and getting some other numerical result. I could ask for what's the expected value of cosine x, what's the expected value of e to the x, right, all those kinds of things. All I have to do is plug in the corresponding function in front of the PDF before I do the integral. Questions? Comments? Okay, so one of the most important things that we often care about is the variance of a random variable, right? That's the main application of these kinds of functions of a random variable. So, a common special case is the variance of a random variable, which we've already defined before, right? Remember that the variance of a random variable is basically a measure of how far I expect x to be from its mean, right? So this mean, sometimes I call it mu, or we could call it e of x, right? Same thing. And this is always going to be a positive number, or at least a non-zero, or a non-negative number. And if I plug in, the definition here, this is like saying, okay, the expected value of this function is t minus mu squared fx of t dt. Now I can do some separation of these terms, t squared fx of t dt minus 2 mu times this integral plus mu squared, I'm sorry, 2 mu times t, mu squared times the integral by itself. I'm sorry, I got this a little bit squished here. All right, so let me read it for you in case you can't read it from the back. So I've got an integral t squared f of x t, then I've got a minus 2 mu integral t fx of t, then I've got a plus mu squared integral of just fx of t by itself, dt dt. So this first part is the definition of the expected value of x squared, right? That's what I, kind of just told you over here. I'm putting t squared in place of what I want to, what I normally put t. So this is the expected value of x squared. This is 2 mu times the expected value of x, right? This is our definition of this. This here is mu squared times this integral of the PDF, which is just going to be 1, right? Because I know the PDF has to integrate to 1, so I have mu squared by itself. And remember that mu is itself, e of x, right? So basically I have this. I'm just going to substitute in what I mean by mu. And I can see that what I get at the end is expected value of x squared inside the parentheses minus the mean squared, which we already knew about from discrete random variables, right? This is not, again, a new definition, just remembering that this is, you know, how it works. So again, if you're asked to compute the variance of a random variable, you can either do it directly like this, which sometimes may be easier given how the integral seems to be looking, or you could do it like this, where first you compute the mean, then you compute the expected value of x squared, and then you subtract one from the other, right? And so, you know, we're going to do some examples of this in just a second. Here I'm using some of the same properties of expected value that I already knew about, right? So for example, remember that if I have the, you know, let's say properties. Remember that I have the expected value of, like, you know, ax plus by. I can take that apart into a times e of x plus b times e of y, right? So this is basically what it means for this expected value to be linear, a linear function, right? And I've already kind of done that here in the sense that I took apart this sum into a bunch of separate, you know, integrals. That's exactly what I was using. And in the same way, if I have expected value of x plus some constant, that's just the expected value of x plus that constant, right? The constant part isn't random, so it doesn't, you know, have to get expectified. That's not a real word. Okay, so another note, just kind of following on from this, one thing you may remember from discrete random variables is that, you know, what is the variance of something like this, ax, right? Well, let's write down what this means. This is like the expected value of ax squared minus the expected value of ax squared. So here I can pull out the a squared, and I can pull out the a squared over here too. And so what I get is a squared times the variance of x. So this may be useful on the homework and in other stuff too, right? So you don't have to necessarily crank through the variance. If I see something that is basically, you know, the variance of a multiplied, you know, variance of something I already know multiplied by a constant, I can just take that constant out and square it. And in a similar way, the variance of some random variable plus some constant is just the same as the variance of the original random variable, right? That's like saying if I take the PDF and I shift it down the axis a little bit, that doesn't change its natural spread, its natural deviation from the mean. I'm changing the mean when I do that, but I definitely don't change anything else about the shape of the distribution, right? So I can just throw that constant away when it comes to variance. Okay. So like I said, the more mature that you guys become, the less I'm going to make you do lots and lots of integrals, and the more I'm going to expect you to just kind of be able to use these probability properties without sweating it too much, okay? So just for the sake of argument, let's compute the variance of that distribution that I was using before. So what is the variance of this guy from before? Well, from previous sheet, I know that the mean is 1.5. What is the expected value of x squared? Well, it's going to be the integral from 0 to 2, t squared times 3/8 t squared dt. So now I'm going to have 3/8 t to the 4th power. So that means I'm going to have 3 over 40 t to the 5th, evaluated at t equals 2, t equals 0. So when I plug 2 in there, I'm going to get 32 times 3 over 40, which is, let's see, these things are both multiples of 8, right? So I'm going to have 12 over 5. And so the variance of this random variable is e of x squared minus e of x squared. So I get 12 over 5 minus, this thing squared is 9 over 4, which is going to be 48 minus 45 over 20, which is 3 over 20. So, not too bad, hopefully. Move this up a little bit. So again, if you do the variance computation and you come out with a negative number, you probably did it wrong, right? Because variances are expected values of this square, so they always have to be 0 or positive, right? Again, don't forget that these two things are not the same, right? The expected value of x squared is not the same thing as squaring the mean, which we saw right here, right? If that was true, then the variance or random variable would be 0, and we know that's not true, right? So don't make the shorthand mistake of pulling the square out of the parentheses. That's bad. So one of the things I'm asking you to do on the homework is compute the variance of the uniform random variable, which is a little hairy, but not horrible. That's a good homework problem. And you know what it's going to be from looking at the answer in the book, but maybe you don't know how you're going to get there. So that's a good, 10-point homework problem. Let's just, for the sake of our, well, let me stop and ask. Questions or comments about this stuff? All right, so let's just prove that the variance of the Gaussian was in fact what I said it was, right? I know it's going to be sigma squared, but why is that true? So let's do, what is the variance of the Gaussian random variable? Well, remember, what is the PDF? It is 1 over square root of 2 pi sigma e to the minus 1/2, 1 over 2 sigma squared, sorry, t minus mu squared. Okay, so what is the variance of x? So here, I'm going to do this directly from this definition, okay? Because I've got an x minus mu here, I've got an x minus mu here, so I have some intuition that maybe I should just keep things with x minus mu. So what I'm going to do is I'm going to integrate from minus infinity to infinity. I have t minus mu squared times 1 over square root of 2 pi sigma e to the minus 1 over 2 sigma squared t minus mu squared dt. Looks kind of like a mess. Well, one thing I can do is I can move the guy out here. I can also do a quick change of variables because I know that shifting things by the mean is not going to change this computation, right? So I'm just going to do a quick change of variables from t minus mu to t to make everything kind of nicely centered in the middle, making for a nicer looking integral. Although now this is also still not like so exciting, right? Life would be great if this was a t here, because then I would have the derivative of the t squared in the exponent, but no can do. So this leads me to another integration by parts. Ooh. So what do I got here? I'm going to, again, try to get this t e to something in a term by itself. So let's make my little map here. So the dv, I'm going to take one of the t's and the dt part, and that leaves behind for u the other t, which means that du is dt. And then v, what do you call it? Integral, right, of this is going to be, let's think about this for a second. So I've got the t that I need. I think the v is going to be minus sigma squared e to the minus t squared over 2 sigma squared. Let's make sure that's true. Well, the derivative of this with respect to t is going to be 2t over 2 sigma squared. So I'm going to basically have the 2's canceling out. I need to get rid of the sigma squared, and I get the t. Okay, that should be okay. So then what is my uv minus integral v du? uv is t, or let's see, minus t sigma squared, e to the minus t squared over 2 sigma squared, minus the integral v du. So I'm going to get sigma squared e to the minus t squared over 2 sigma squared dt. All right. And this thing I have to evaluate at minus infinity to infinity. Sorry for this mess. Well, again, let's think about this. This is, again, saying that I'm going to plug in infinity to here, and I'm going to get something that is super duper small, right? E to the minus infinity squared is pretty small. That's going to be much, much smaller than this big infinity here. So no matter which infinity I plug into here, these are both going to be 0. So then I'm going to get this integral, sigma squared e to the minus t squared 2 sigma squared dt. And now life is pretty good, actually, because this here is going to be, let's not forget I have this guy hanging around here. So actually, there's this factor out here. What I have is 1 over square root of 2 pi sigma times this integral, sigma squared e to the minus t squared 2 sigma squared dt. If I put my finger over this, this here is exactly the original PDF, right? So all I have is this leftover sigma squared, and that's exactly what I wanted to get, right? So basically, this is the PDF of the Gaussian by itself originally, and I have an extra factor of sigma squared. So success. Dramatic finish, right? Again, I don't expect you to do this on the exam, but this is just kind of like verifying that, in fact, what I called the variance is indeed the variance, okay? So life is good. So again, the main thing is not to be an exercise in integration, but there are a couple things that I keep on using here. So one is that whenever I spot that I'm doing the integral of the PDF, I know I can simplify that immediately to 1, right? That's kind of a good trick to observe. And whenever I have like the integral of t times the PDF, I can immediately turn that into the mean. Those are the kinds of things that you should be looking out for, okay? Okay. Comments or questions? So what I want to spend the last 15 minutes or so doing is a engineering application, okay? Just for those of you that are actually interested in electrical engineering, right? This is what this course is supposed to be for. So let me do an example of something that you may have come across in engineering, which is called designing quantizers, right? So this is kind of like an application of all this stuff. Right, a quantizer is basically saying, you know, this is a big thing in signals, right? We've got continuous time signals and discrete time signals. That's kind of like how do we split up things on the time axis. But also in the real world, we can't represent a signal with infinite precision on the y-axis either. We have to make a decision about how to round the signal to one of a set of values, right? And so this is what gives rise to like 8-bit audio or 16-bit video, something like that, right? And so just a quick show of hands, who has heard this electrical engineering phrase 6 dB per bit? Oh, nobody? Maybe you heard it here first. So let me give you a quick overview. Again, this is like a little bit of a side note, so don't worry about this too much. But just, you know, what you're trying to do when you're quantizing is that you have a before and after, right? So you have the original value of x. And again, so far we're not talking about anything random yet. This is just like the x-axis, right? And then we have a function of x, which is the quantizer, okay? And so there's something called a uniform quantizer. Okay? So let's suppose, for example, I'm going to tell you, okay, no matter what your signal value is, I'm only going to give you 8 levels to quantize it at. And what should those 8 levels be? Okay? So let's suppose that this x is distributed between some maximum value, right? plus or minus x max, okay? Well, what I'm going to do as a first guess is say, okay, you know, you only get, I'm going to mark off the kind of half and quarter waypoints here. So a uniform quantizer says, okay, if I'm between, say, 0 and this x max over 4, what I should do is I should round everything to like this halfway mark, right? That seems to make the most sense because then, you know, I'm pretty close to the halfway mark in general, and then my next step looks like this, and then like this, and then like this. And then kind of on the other hand, I have something that looks like this, like this, like this, and like this. Right? So this number is like x max over 4, and then this level to which I'm rounding is x max over 8, okay? So this would be a, what we call a uniform 3-bit quantizer. Why is it 3 bits? Because 2 to the 3rd power is equal to 8, right? So normally we talk about, you know, bits, and then we raise 2 to that power. So this is like saying I have a 3-bit quantizer. So if I call this value n, then the actual number of levels I have is 2 to the 3rd equals 8, okay? So we have basically n bits per sample is the way to think about it, right? So if I'm allowed to do 3 bits, that lets me do 8 on and off patterns, okay? Okay. And so what did I do? Basically, you know, one thing that I did here is I said, okay, well, you know, let's assume that the input random variable is uniformly distributed. Right? That's like saying I basically have an equal chance of being in any of these 8 intervals, okay? And within each interval, I am basically choosing the halfway point between the both ends of the interval, okay? So if the input is uniformly distributed, then the error that I'm making within an interval, so then the error in each interval is also uniformly distributed, the quantization error, that is. And that's going to be an error. How much error could I be making, right? Well, basically, you know, consider this small interval here. You know, if I'm quantizing to x max over 8, that's the biggest that the error can be, right? Because if I'm at 0, I have an error of negative x max over 8. And if I'm at x max over 4, I have an error of positive x max over 8. So basically, I have an error of x max over, let's just call that x max over m, right? That's the number of levels I have. Okay. And then, hopefully, at least you've heard of the signal-to-noise ratio, right? So this is like a kind of a thing that we want to know is, okay, so how much noise am I introducing? It seems clear that the more levels I have, the more faithful the quantized signal will be to the original signal, okay? So what is the SNR, signal-to-noise ratio? Well, for, you know, weird historical reasons, we define it in terms of dB, right, decibels. Now, I guess maybe you're certainly going to hear about this in signals. You probably haven't gotten there yet, but certainly when you come to doing like Bode plots and stuff like that, you're going to be talking about dB. So the signal-to-noise ratio is basically more or less defined as the ratio of the variance of the original signal over the variance of the error. Right? So what is the variance of the original signal? Well, this is a uniform distribution on plus or minus, minus x max to plus x max. So let me just kind of do a quick aside. So as you'll show on the homework, the variance of a uniform distribution on A to B is basically 1/12 B minus A squared. This is one of those book formulas that you're going to prove on the homework, and then you can use it forever. I give you permission. So what is this going to be then? So the signal-to-noise ratio is going to be 10 log 10 of, so the variance of X is going to be 1/12 B minus A. I'm going to have a range of 2x max squared. And then the variance of the error is going to be in this range, which is going to be 2 over m x max squared. These 2's are going to cancel each other out, and I'm going to get, and the 1/12s are also going to go away, and the x maxes are going to go away. Basically, all I'm going to have is log 10 of m squared. M is the number of levels I have, and I defined m as 2 to the n bits, right? So this is going to be, you know, if I have a 3-level quantizer, n is 3, m is 8. So now what I get is 20n log 10 of 2. Log 10 of 2 is approximately 0.3. This is like another kind of handy engineering fact. So then what I get is 6n, more or less, approximately. So why is this interesting? Right, this says that for every extra bit I give to my quantizer, I gain 6 dB in the signal-to-noise ratio, right? That tells me exactly how much better I'm doing every time I make the quantizer a little bit better, right? That's why 8-bit audio, or that's why 16-bit audio sounds so much better than 8-bit audio, right? It's like adding 48 dB, right? So the things should be much more faithful. So this is where, if you ever hear anyone tell you 6 dB per bit, that's where it comes from, okay? And in some sense, you're getting kind of a double bang for your buck, because every time you add an extra bit, you double the number of levels, and you have the number of, or you have the width of the error, so life is getting better. Okay. Now let's tie it back. Why are we even talking about this in probability class, right? This seems like, okay, we use the variance of the uniform distribution to get here, but what does this matter for kind of real world quantization? The interesting part, or at least it's interesting to me, is what happens when you don't have a uniform distribution, right? One thing that we know in the real world is that signals are very rarely uniform, right? So if I've got a voice signal, for example, it's going to be very strange that the amplitude of that voice signal is going to be uniform statistically. It's probably going to look more like a Gaussian or some sort of weird shape that is close to 0, and it's got some long tail, right? So the problem is that, let's just say, you know, in the real world, most input distributions aren't Gaussian, or aren't uniform, sorry. Right, so let's suppose, for example, I had an input distribution that instead of being uniform between plus or minus x max, let's suppose that it looked something like a Gaussian, right? Doesn't have to be very equally spaced here. So here, if I was going to apply my uniform quantizer to this distribution, what I would be doing is I'd just kind of be following my nose and saying, okay, suppose I was going to apply an 8-bit quantizer to this distribution. I would say, okay, you know, more or less what I'd be doing is I would be quantizing all the stuff over here to, you know, this value, and all the stuff over here, this value. But what am I doing? I'm throwing away a great opportunity, right? So this is like saying, okay, a uniform quantizer kind of assumes that all of these bins are equally likely to happen, right? And I can see here that for the distribution I drew, that, you know, suppose that the quantizer level out here was, you know, if I'm going to label these by like binary code words, you know, my underlying assumption is that all these code words are occurring with relatively equal frequency, right? But I can see from this picture, from the PDF, that I'm hardly ever going to use these code words 000 and 111, right? Those are like way, way out at the tails of the PDF. And I'm going to be wasting my potential because these code words here are going to be getting used all the time, right? That's where all the probability mass is. And so the intuition is, well, I should put the divisions on the x-axis in a non-uniform way, right? What I should be doing is trying to kind of make each of these intervals equally likely, right? And how would I do that? Well, I would basically have to go through this PDF and chop it up in such a way that each of the chopped areas would have the same probability, right? So the idea would be to put breakpoints to divide the PDF into equally probable regions. You kind of got a flavor of that on one of the homeworks, right? There was a homework where I asked you, how could you chop up the exponential distribution so that there was half of it on one end, half of it on one side, half of it on the other side, right? That's a way of, suppose I just had like 2 levels, that's like a 2-bit or a 1-bit quantizer for the exponential distribution. That would be the place where I should draw my line, right? And so what would that look like in this case? It would look something like this, right? So if I have lots of probability mass, probably what would happen would be that I would draw, you know, a level here, and a level here, and a level here. Again, maybe drawing is not super to scale. But the idea being that, you know, in this area, I have an eighth of the probability, and this area has an eighth, and this area has an eighth, and this area has an eighth, right? That would be the smarter thing to do. And then what I would do in each side of these areas is I would find the best quantization level to use, okay? So this would be non-uniform quantization. And so in the interest of time, instead of like going through and proving what's happening, let me just say what the upshot is, right? So the right thing that you should do, is, number one, I should place the, you know, I guess the breakpoints to evenly split up PDF into equal probable regions. And then I should set the quantization levels to be the conditional mean inside each interval. Right? What I mean by that is it's like saying, okay, if these are my breakpoints, right? So say this is like breakpoint k and breakpoint k plus 1, what I should do is I should let my reconstruction level, say yk, equal the conditional expected value of being inside that interval, something like this. right? The bottom is basically just like the probability of being in this interval, and the top is what is the conditional mean, or the whole thing is the conditional mean. This is just like the expected value divided by the total amount of probability, right? So this is sometimes called, you'll see this called lloyd-max quantization, or if you've ever heard of a compander, which stands for like a compressor expander, that's what this is. So again, if you were to take a course like digital communication signals, or digital communication systems, or something like that, or if you're interested in audio engineering, these are the kinds of things that you will come up against, right? So again, this is really totally aside from mainline probability. You're not going to get any homework or exam questions on quantization, but it is kind of an application of, why do we care about probability in signal processing and electrical engineering, right? This is a common thing to want to do. And so if you were to take DSP from me, we would be doing this in the 4,000 level DSP class. Okay, so that's about it. I will see you next week, and have a good week.